Okay, so let's finish the last few slides. I'm going to explain some more terms and terminology so that I hope you can understand some concept, and you just need to find the algorithm for this method and you can completely understand all of this. Okay, so in here, the code here is split in two cases. One is slow down and another one is not slowing down. So if in the case that not slowing down, if the robot is still far from the destination, okay, and so here is the way to find the center of the circle, PS, okay, center of circle. So these two cases is to make sure that whether you are on this side of, okay, this side of the destination or this side of the destination. If you are this side of destination, its rotation on the circle must be different. Oh, sorry, it should be like this and then rotate like this. So the rotation is on counterclockwise, but if you are this side, the rotation is clockwise. and and here is the norm of distance from the location of robot to the center of the circle. So if it is less than curve zone, okay, from here to here is less than curve zone, it means yeah, I mean actually it fall into the case that when you are on the circle itself. Yeah, this is to you for when the robot is on the circle itself, but actually even though if condition is given like this happen after this else happened before. So here d is the distance from the location of the robot to the circle, okay, and alpha is the angle of between vector from S to the center of circle and the vector d that from S to the tangent point on a circle, right? This is alpha. And phi actually is just an angle, the orientation of uh, vector S to the center of circle, right? This is phi. So then we can define orientation of, no, I mean vector, not or just orientation, but the vector itself from S to the tangent point, okay, by adding the vector from 0 to S, and then from S to this point. From S to this point, we have magnitude d, and then cosine the angle with respect to x-axis, and sine of the angle with respect to y-axis. Okay, so U2 actually is yeah, U1 and U2 actually it just if the circle is on this side. I mean, if alpha is not added up to 5, but instead the angle to the u vector is defined by phi minus alpha. That's why we must define in the case of u1 and u2. And this condition is to check whether actually we can say the rotation is supposed to be clockwise or counterclockwise. So for this case, the rotation is clockwise. For this one clockwise, this one for counterclockwise. The position S is up there. Okay, something like that. And M is the midpoint between D and S. So midpoint D and S. So destination is here. Yeah, M is still here. And SDV, so is the vector from S to D. And then dv is the norm, or is a unit vector, sorry, unit vector of from here to here. Okay, so we can have unit vector as dv. Oops. Unit vector dv, and from, okay. So actually, this is a mistake. This is a mistake. Actually, D is changed from the actual, I mean, the final destination to be D here is defined by on, yeah, D is on the tangent circle. Okay, so capital D is changed. Okay, during the line segment, destination is supposed to be at the tangent point on the circle. So I'm actually midpoint here. So is midpoint here. Um, well, so if norm 2, which is a distance of norm 2, L2, I mean L2 is the norm of SDV. So L2 is defined here before. So it means the distance from S to the final destination is greater than, yeah, greater than accuracy. So velocity is set uh, to be increased at maximum acceleration. Okay, and if velocity is greater than Vmax, we constrain it to be just Vmax. We cannot let it higher than maximum. And then here EV is a vector from uh, yeah, from robot location to the new destination on the circle. Okay, that is EV. And DTV, yeah, so actually yeah, so in the case of motion along this line before it switch to circle, EV and DV are the same. Okay, EV and DV are the same. So this the how, what to say, the cross product between these two vectors is supposed to be zero, right? So here if it's smaller than the some threshold value, then SV, the norm value of the unit vector of SDV, I mean unit vector from the location of the robot to the destination. Okay, is defined by this way. And then in the case of a different case else, I mean when it's on a circle. Okay, when on a circle, we set up. So LC means if the cross product between these two vector, because when it's on a circle, the destination D, okay, destination DV, sorry, DV is different. Okay, dv here is different from d minus a. So cross product between two vectors which are not parallel must be large, not close to zero anymore. Uh, Not zero anymore. So we set the parameter for, okay, for moving along the circle. So at this part, I'm not going to explain the detail. Um, so just want you to know the section that separate from one case to another case, and what happens along from each time from one moment to another moment, especially before it switch from the motion on the segment to the motion on circle. So after everything, so the velocity, linear velocity and angular velocity are set according to the control law. This follow the control law. Um, okay, so controller is combined together by U, and then here is the kinematics. Kinematics equation that computed using Euler integration, Euler method. Then we can have the position of the robot. So in order to simulate this algorithm in a similar way, let's say you can, as long as you know the location of robot, I mean, uh, you know the location h and y of the robot, so h and y, and also the orientation phi. So you can plot the robot body accordingly to this known parameter. So this h by phi is computed by the last equation. I mean, actually, yeah, to be precise, this q. So q is h y and q is h y and phi. So from this, for phi you can construct orientation or rotation matrix. H and y you can construct the origin of the robot. So with this information, you can plot the robot at a certain location. Okay. So in order to simulate this, it's better to have a code to draw the robot body, and this robot body is plotted according to the location of the center and the orientation described by rotation matrix. So you can test this algorithm and see animation of robot motion, something like that. Um, so actually, the input of the this code actually are all all here before the loop. So if you want to simulate uh, inside the loop here, you don't need to change anything. But outside the loop, you can change the parameter according to your simulation scenario. Okay. For example, maximum acceleration, it is constrained to the actuator capacity. Okay, velocity is same, and accuracy depends. Yeah, accuracy. I think once you choose maximum velocity, that's okay. Curve zone, it depends on your robot. So what is the diameter of the circle that you think your robot can turn around? All right. So you just change different parameter here before the loop, and then you can implement the code by this loop. And if you have another segment of code to animate the motion of the robot, that will be easy for you to make conclusion on the behavior of the simulation. Do you think you can do it? Actually, yeah, because the code, you don't need to understand the detail. I explained some concept so that you can extend it to understand it more deeply if you want to. But just for simulation, I just want you to understand some key points. So first, set all the parameters. Set all the parameters before the loop here according to your simulation scenario or experiment scenario. and then you can implement if you use Simulink, then you drop out the loop for. You don't need to use the loop for, but you take everything inside the loop for, put into a Matlab function. Okay, and when then the output of your Matlab function would be Q. Yeah, what you need actually for the output of, oops, yeah, this Q must be the output, and from information of the Q, you can build a set of code that can animate motion of the robot. That will be good. Have you ever tried a code for animation in Matlab or something? Just give you an idea. For example, in this robot group, um, yeah, what I was asking is about this. Let's say you draw you make set of points for robot body, and you draw connects those points to be a frame of the robot. Okay, um, so the coordinate of this all of set of this point will change according to its origin and orientation, right? So the orientation, the rotation matrix, you apply to transform coordinate from body frame into global frame or something like that. Oh no, if you have orientation, yeah, that's right. Actually, that's right. You know the orientation. You apply it to the set of the frame of the robot. Okay, using rotation method to transform it into the global frame. Then you can change the coordinate like that, and then you add those coordinates by the origin H and Y that computed by Q, and then you have the shift of robot to something to the other place accordingly, right? And if so, in the loop of you plotting this robot in Matlab, is you run a loop, you plot again and again. It's very fast. Then if you post some small amount of times, then you get this animation. Okay, and yeah, in Matlab you can use background image. Just if you want the actual image, you just cut it and plot it together as a background. Yeah, that's it. Yeah, just give you some ideas. Here, let's see the performance for this control algorithm. So we can see that the velocity. Okay, so velocity can increase by acceleration, a certain acceleration to maximum when it is still on approaching the tangent point on the circle, right? I mean the motion is almost linear during that phase. So velocity jump to maximum, and then when it reaches the goal, it just fall to zero. So velocity always maximum. That's interesting, eh? Linear velocity always maximum. And for angular velocity, you can see that angular velocity first because it's spin in the direction of negative. I mean same as clockwise. So it falls to some certain value of negative, and then uh, it increase. No, this is velocity. Okay, so it means when it almost reach the right the right orientation, the velocity of orientation start to approach to zero. Okay, we converge to zero. But when the transition from the line segment to circle, the angular velocity change by a lot. Okay, start to change here. You can see, and so here it depends on the radius. The higher the radius, the smaller the chain. Okay, if the radius is too small, and then it changes sharply. And in the case of differential wheel, if you change from we change at one point immediately, so the chain look like a spike, right? Because for one point, okay, waypoint, this point to this point, and then to another point. So the chain at the intermediate point, the chain is like a spike. It change instantaneously to certain value by a lot in very short time, right? So this one somehow it change smoothly, even though it changed by a lot, but it goes smoothly. All right. So is there any question? So actually, I only pick up two. I only pick two algorithm that you can that is more likely to be practical because the chain of angular velocity is somehow smooth. Then if you implement with hardware with actual robot, more likely it functions well. Okay, so if no question, then we can end our lecture now.